Okay, so in this lesson, we're going to discuss acidification. I know that in the greenhouse we started adding some acids to adjust the pH, but let's go into some depth here as to what is going on. Um, so as far as media is concerned, we've talked about pH and CEC before in Plant Science 2. And we've talked about how pH has to be in the proper range and how cation exchange capacity is helpful. This is with peat moss and coir, not so much in hydroponic production. But sometimes you're growing in coir and peat moss and there is actually some CEC, but for the most part, let's just treat hydroponics as being whatever we present to the root zone is what it gets. And then we have to make sure that we don't have soluble salts or ECs that are so high that they damage roots, right? In dry down parts of the day where the plants are drinking lots of water, right? So pH is critical because it affects the availability of nutrients. We talked about that in one of the other lessons. Typically, peat moss has lime added to bring the pH up because peat moss is generally acidic. This is why a lot of things are preserved in peat bogs because the pH is so low, it prevents bacteria from growing. In hydroponic crops, we typically want to have a lower pH. We've talked about this before, in the 5.5 to 6 maximum. But the sweet spot is around 5.6. And we have options like nitric acid, phosphoric acid, sulfuric acid. Which acid depends on your needs and dollars. We're going to get into that now. As far as nitric acid is concerned, it's considered a strong acid. It's also fairly cost effective. And because it's strong, we don't need a lot. Typically, in agricultural context, it's around 67% concentration, which will burn your skin on contact. It'll hurt. It's not going to kill you, but it's going to give you a burn. So most important thing to remember is if you're ever in this situation, I can't see how you would be, but you always pour acid into water, not water into acid, because it will boil and then that will cause bubbles, which will splash the acid up and into your face. This has happened in the past in like pools where they're adding muriatic acid and the person monitoring the pool doesn't realize and they manage to get water into the muriatic acid bottle and then it turns into water and steam and bursts and you're covered with acid. It's horrible. So always pour acid into water, never reverse. The other thing about nitric acid is that it gives off fumes that are corrosive. You do not want to inhale that. That will burn your lungs. Or if you have a tank and you leave it open, the fumes will actually attack any metals that are within 15 feet of the tank and start causing huge amounts of rust. As far as what happens with acids, nitric acid, typically 1 mole of nitric acid is equivalent to 1 mole of acid. So that's helpful for thinking about when we're looking at how many millimoles of acid will we need to neutralize how many millimoles of bicarbonates. And so if here we have nitric acid and it dissociates into 1 proton, right, and 1 nitrate. And this is really helpful because, first of all, the proton gives us the acid that we need to neutralize any alkalinity, and we're left with a nutrient that plants can actually consume. So there's actually a nutrient that's in there, nitrate, which is very useful. Phosphoric acid is typically a weaker acid. It's sold at a slightly higher concentration because of its weak acidity. It's safer. It's also more costly. And it does add phosphate, which is a nutrient, right? That's helpful. But that does come at the cost that phosphoric acid, the phosphate will react with calcium. So if you have a high calcium media, that will actually form precipitates. Sulfuric acid, which is quite strong, it's probably one of the stronger acids of the three, does not add a significant nutrient. Sulfates are not really that useful to the plants. There's more than enough sulfates in most nutrient solutions, so we're not looking to add more necessarily. But it is very strong and it's inexpensive. But it is also a problem in the sense that it reacts with certain fertilizers. So it's not compatible with calcium, so we got to be careful about that. So both phosphoric acid and sulfuric acid have their problems when it comes to reacting with nutrients. Citric acid, which is another one you might run into, especially if you're trying to grow organically, this is one that we'll try using, but it's a weak acid. It's a very large molecule, and of the 3 protons, it's really just this one that comes off. So you've got all this big molecule for one little proton that's coming off. That's not overly helpful. But it can be used in organic contexts, depending on how the citric acid was derived. So it's something you might run into. One interesting side effect is that that big molecule has antimicrobial properties, which may or may not be a good thing, right? So think back to the context of what I just said about organic production, right? If it's antimicrobial, what if it is damaging to beneficial bacteria? So that is something really important to keep in mind. Now, I have not included in this lesson vinegar, and that is for a reason. Acetic acid is not used. First of all, it's a weak acid, and on top of that, bacteria consume it. So if you use a lot of vinegar as an acidifying agent, you actually get sort of slime in your solution because you're growing bacteria. You need a lot of vinegar to be bacterial static to stop bacteria from growing, and those kinds of vinegar levels will damage your plants. So generally speaking, vinegar is not suitable for adjusting pH. I know that might go contrary to some YouTube videos you've seen out there, but not a great idea. It's going to grow bacteria that are going to cause problems. You're going to end up with root diseases. You've seen this many times. I don't want to overemphasize this, but again, for water or hydroponics, we're looking at a very different pH availability, right? Here's your green zone. I'm going to say it's in this area, but right here you can see manganese deficiencies are going to be a problem anytime around pH 6. So we try to keep it closer to 5.5 if we can. But more often than not, manganese is an issue, more so than iron with pHs. And some crops can handle it, some don't. Typically we're supplying at a larger volume so that it's okay, but be mindful of that. If you start seeing manganese toxicities, then you need to back off. As far as pH and alkalinity, it's vitally important that we keep the pH in the right area, and how we do that is by dealing with alkalinity. So alkalinity is sort of like the opposite of pH. I mentioned this in one of the earlier lessons where I talked about bicarbonates. Typically they're reported with water tests in millimole, but I have seen it in ppm. I've got a slide coming up that shows the college analysis, but if you remember from that other lesson, here we have bicarbonate is like the Pac-Man floating around, eating up the protons, right? So once all the protons are eaten up, whatever's left, say all the bicarbonates have been used, 1, 2, 3, 4, we have a few protons that are left. In this case, you got one here, and you got one here. So there's some acidity left. So ideally, we have a certain amount of bicarbonates there, but not so much that all the acidity is used up, and that's usually 1 millimole is our target. So as we increase bicarbonates, pH goes up, right? And as we consume all the protons, the pH goes higher and higher. Having some bicarbonates is beneficial in the sense that it will buffer. You'll see this line is a little flatter around the pHs that we're talking about here, but it's not perfect. But having some bicarbonates will help us buffer. That means that the water will resist changing pHs quite as much as it would without any buffering. So typically 1 millimole of bicarbonate is what we're looking for. So where do we get bicarbonates from? In groundwater, it comes from limestone. It's almost always from limestone. So if you have a well that has lots of limestone, so in our area in Niagara, with the escarpment, there's lots of limestone. We tend to have higher pH water. And of course, if you have rivers that are running over that limestone, you also get hard or calcic or bicarbonates in your water. And city water often depends on where you get your water from. In our area, the city water is derived from Lake Ontario, which has a limestone bed. So obviously it's got lots of bicarbonates. If, for example, your city water is from river water, it would depend on where that river water is flowing. But a lot of our water down here has a limestone base. Parts of northern Ontario have a lot of granite in the lakes and in the rivers, and that is acidic. So less bicarb. Sometimes you have to add some bicarbonates to make sure the water has some buffering. Otherwise, your pH is constantly all over the map. And some of you who are growing with fancy RO water might find that your pH is really hard to dial in, and that's because you don't have enough bicarbonates to buffer it. This is a snapshot of bicarbonates in a water test from Niagara College. This is about 5 years old, but it's city water, so it's pretty constant. And we're looking at around 1.9 millimoles of bicarbonates in our water. And the pH is 7.72. We don't want that. We want the pH down closer to where it's at 5.6. Okay, so that pH is too high. And we have a bicarbonate concentration of 1.9, and we have a target of 1 millimolar. So we need to gobble up 0.9 of excess bicarbonates. So we have to react them with protons. Just like that Pac-Man slide. We need to consume 0.9 so that we're left with 1 millimole. All right, so here we've got one proton from an acid dealing with one molecule of bicarb that's going to react and produce carbon dioxide and water. That's all you get when you consume it. Just like pop, you get fizzy water. If you add enough vinegar and enough bicarbonate, you get lots of fizz. We've all done that with vinegar and baking soda because baking soda has sodium bicarbonate. So when you add the vinegar to the baking soda, it produces CO2, and that's how our muffins and our cakes rise when we make that reaction in the dough as we bake it. So the same thing's happening with the irrigation water. We're adding an acid, in this case nitric acid or phosphoric acid, and it's going to react with the bicarbonates to produce CO2 and water, and that consumes protons. And that means our pH will adjust, okay? Typically, nitrogen, phosphoric, add nitrogen and phosphorus as a nutrient. Mention that. That's not a bad thing. But you also don't want to have reactions. In this case, this is a drip plug dripper that has reacted with phosphate. I was just discussing with Matt. I think at the college, normally we use nitric acid in our solutions, and I noticed that there was phosphoric acid hanging around. That may be the reason why some of our drippers are plugging, because this is what a dripper looks like when phosphoric acid reacts with calcium. If we're just using 2820, it doesn't have as much calcium. Remember I mentioned you have to rotate it with 14014 to get enough calcium for certain crops. So if you're just using 2820 in the nutrient solution, phosphoric acid works. But when we use a complete nutrient solution like the one we're mixing that has high calcium, it forms these insoluble molecules that plug drippers, and that might explain why we've been having some challenges. So we have to make sure we're using nitric acid, not phosphoric acid. So let's look at the problem. Say we're using the water analysis from the college. We want to neutralize our water. In this case, I'm going to bump the number up so the numbers are a little more extreme. Let's say we have 3.2 millimole in our water test, and we want to bring it down to the desired 1 millimole from 3.2 using 67% nitric acid, and we're treating 100 liters of water. Okay? So we're treating 100 liters of water with 67% nitric acid. If we want to have a 1 millimole final, that means we need to neutralize 2.2 millimoles of bicarbonates because we have that much extra. So here's some things that you have to look at when you're doing this math. Yes, math again, I'm sorry. we need to know the molecular weight of nitric acid. That is 63, right? That means that 1 millimole solution is 63 milligrams per liter. All right, and if we are dealing with 67% acid, right, that means 67% of the solution is nitric acid. The other thing we need to look at is the density of acid. That helps us understand how much we need to measure. Because we're dealing with an impure solution, we need to know how many grams per milliliter we're taking up when we measure it from the stock solution. All right, this will make sense as I walk you through the math. So let's start with that. How many moles of acid do you need? Okay, we did that in the other slide. We calculated that we need 2.2 millimoles of acid because that will neutralize 2.2 millimoles of bicarbonate. That's a terrible 2.2. Okay, so we start off with 3.2 millimoles of bicarbonate. We want 1, so we have to take away 2.2 millimoles of bicarbonate, which on a 1-for-1 reaction means we have to get 2.2 millimoles of acid. Okay, so let's move on. How many milligrams of acid do we need? Well, we know that 63 milligrams per liter is 1 millimole, and we want 2.2 millimoles because remember, we're neutralizing 2.2 millimoles of bicarbonates. So we want to add just the right amount of acid to knock out that much bicarbonate. So we're left with the desired 1 millimole. All right, so 2.2 millimoles is what we need. So 2.2 times 63 milligrams is going to give us the end bicarbonate that we need, or the end acid, right? So 63 milligrams per liter is 1 millimole. 2.2 means 2.2 times 63, which means we need 138.6 milligrams per liter final. I hope that makes sense. So the acid is 63 milligrams per liter is 1 millimole. We want 2.2, so we're going to multiply 2.2 times this, 63, which is going to give us 138.6 milligrams per liter. That's what we need in our final solution. All right. Now, how big was the volume of water we're dealing with? If you looked at the first slide, it was 100 liters. So we're treating 100 liters. All right. We just calculated how many milligrams per liter, which means if we're doing 100 liters, you have to multiply by 100, which gives us 13,860 milligrams of nitric acid. So that's how much we need in 100 liters. How do we get that? Let's look at the next step, density. Right? This acid density helps us arrive at how many milligrams we'll get for every milliliter we pull out of the acid solution. So for trying to figure out how many milligrams we need, we look at the density of the acid. And for the density, we know from the first slide that it's 1.4 grams per milliliter, which is actually the same as 1,400 milligrams per liter. And over here, we calculated that we need 13,860 milligrams. So how many times does 1,400 go into 13,860? You take this number, divided by that, it gives us 9.9. That means that for every milliliter, we get 1,400 milligrams, which means if we measure 9.9 milliliters, we're going to get 13,860, which is what we want. Hopefully that makes sense. Here's how I did the math to correct for the percentage. So remember, originally we're assuming it's 100% acid, but in fact it's actually 67%. It's never 100%. 100% would, you'd have a difficult time working with it. It would dissolve a lot of the bottles and whatnot that we're putting it in. It was 100% acid, you open it, it's going to react with any moisture in the atmosphere and react violently. So 67% is safe, which means, of course, 33% is water. So we have to correct for that. So we figured out if it was pure acid, we need 9.9 milliliters. But now we have to correct for the percentage that it is. All right, and here's the math. So 9.9 milliliters is 67% acid. How many milliliters would be 100% acid? And there's the math for you as you see how I've done it. 9.9 times 100 divided by 67, that gives us 14.8 milliliters corrected volume for 67% acid. So this is the sequence of calculations that you would go through for acid correction. So in the course, you're going to have the pleasure of doing this calculation. So I'll give you a question that says, how much acid do we need to add to 50, 100, or 1,000 liters to bring us down to 1 millimole of bicarbonates? And you'll have to recreate this. So hopefully you follow this. I think we're almost done the math in this course after this. So for those of you who are struggling with math, hopefully that brings you some peace. So here's the process from beginning to end. Normally we want 1 millimole of bicarbonate in the water. If we have 3.2, we need to neutralize 2.2. And that means we need 2.2 millimole of acid because it's 1 to 1. All right. 1 millimole of nitric acid is 63 milligrams per liter. We want 2.2. That's going to be 2.2 times 63 is give 138.6 millimoles or milligrams per liter. Then we have to correct for how many liters, right? How many liters was it? It was a 100-liter tank. So we multiply by 100. That gives us 13,860 milligrams in 100 liters. Okay, then the next step was, okay, how many milliliters of acid? Well, we know that acid has a density of 1,400 milligrams per milliliter. How many milliliters do we need to get to 13,800? We did the math, 9.9. Okay, so that means we need 9.9 milliliters of acid, but the acid's only 67% strong, which means we have to correct by multiplying by 100 divided by 67, which corrects up to 14.8 milliliters in 100 liters. If we added 14.8 milliliters of acid to 100 liters, if it was 3.2 millimoles bicarbonate, after the reaction happens, we're left with 1 millimole final, and the water is corrected. So there it is. You can review those slides to help you do the math in preparation for your quiz. And what you'll notice is a very small amount of acid goes a long way. So some of you who have adjusted the pH in the nutrient tanks recognize that we add very small amounts and stir for a few minutes, let it equilibrate, and then check the pH again. If you add too much, you'll overshoot, and then we end up with the pH being way too low, and the crop will experience toxicity effects. This often happens in our cucumber house because it goes through so much water and nutrients that we're constantly adding nutrients in water and adjusting the pH, and sooner or later someone gets it wrong, it swings too low, and we get toxicity, we get brown spots all over the leaves. So we got to be careful with that. Anyways, this is a picture of a tour of some students of mine that were at a Gerbera cut Gerbera house in Jordan last year. They were talking in that lesson, or that tour, about pH being an issue for their crops. They grow in coconut coir, in drip irrigation. All these plants have drippers, and then it goes all the way down to the back, is collected, sent back to the farm, the barn, and recirculated, and pH and nutrients adjusted. So it's kind of like a drip irrigation crop in a sense, but it's cut flowers. So it's not always tomatoes. That's what I was trying to say with this example. So I hope you've enjoyed this, and I hope you bring your questions to me in the greenhouse when I see you next. Take care.